Hi friends, this is probability and stochastic process. I'm Smith, and here the first question is just the introduction and explanation of some simple processes like the first one is the Poisson process. Now Poisson process is defined as now let us first see the distribution of Poisson process. The distribution is given as probability that number of events that the number of Poisson distributed random variable is, we can say that it's just the number of arrivals or number of departures in a specific given interval of time. So the number of arrivals, or let's say number of phone calls that we receive in time interval, let's say number of calls received in time interval 0 to t, it's k. So for this we can say that it's given by e raised to lambda t into lambda t over k upon k factorial, where we can say that lambda is, it's the average rate of receiving the number of calls in this case. So this is a Poisson process, and now if we take a look at if we want to find the mean of such process, that's the expected value of such a process, the mean or the expected value of such a process can be given as, now let's try to find the mean of it. So we find its expected value. So expected value for such a process can be given by, let's say x of t, it's the Poisson process. So the expected value is given by, we differentiate this function with respect to lambda t, so the expected value for this is lambda t. Now let us try to find some useful properties, that is autocorrelation function. So the autocorrelation function for such a process is given by r t1 t2. So this is nothing but at time t1 and t2 they compare the outputs, and we have the autocorrelation function as lambda square t1 t2 plus lambda into minimum of t1 and t2. That is, if t1 is less than t2, if t1 is less than t2, we'll have the autocorrelation function as lambda squared t1 t2 plus lambda t1, and if t1 is greater than t2, then the correlation function can be given by lambda squared t1 t2 plus lambda t2. One more interesting thing about the Poisson process is Poisson process the mean is equals to variance is equals to lambda t. That is, the average increases linearly with time. So the longer we wait, or the longer the interval, the higher probability of receiving the number of calls. So if t is increased, so in this example, if we increase the interval, if we increase the time, that is, longer we wait, we have the higher probability of receiving more calls. So this is Poisson process. Now let us try to see some more process. That is, the second is Poisson increments. Now Poisson increments is defined, we define a stochastic process something like a non-decreasing function, that is, there are few increments. Now let us say that this is the time interval epsilon, and this is t1 minus epsilon, this is t2 minus epsilon, this is time, and this axis is the function that we are going to define, that is Poisson increments. So here this is time t1 and this is time t2. So now let us define a Poisson process. Let us define the Poisson increments. Poisson increments, we can define it as something like y of t as this is x of t plus epsilon minus x of t divided by epsilon, where epsilon is some positive number and it's a given constant. Now for such a process, now let us try to view the distribution of such a process. So the Poisson increments has the distribution something like y of t, which is given by n and by epsilon. N can be viewed as the number of calls in the time interval. So this can be given as y of t into epsilon. From this we can say that it's x of t plus epsilon minus x of t. So this is x of t plus epsilon minus x of t. Sorry for now we have one more process here. Instead of k, here we have n, so it's just the replacement. So the distribution of Poisson increments is e raised to lambda epsilon into lambda epsilon raised to n over n factorial. Now let us try to view the properties related to this Poisson increments. First is the mean or the expected value. Now here n can be viewed as let's say the number of calls in time interval t plus epsilon, t to t plus epsilon, where epsilon is some given constant greater than 0. So let us try to find the mean of such a function, that is y of t. And we know that y of t is x of t plus epsilon minus x of t by epsilon. Epsilon is a constant, so we have to find the expected value of this, and we already know the expected value of the Poisson process. This is the Poisson process, so it is lambda epsilon and it's just the lambda. So the mean of the process that we have defined here, that is Poisson increments, its mean value is lambda. Now let's try to see what its autocorrelation function is. So r t1 t2 can be given as e of y at t1 into y at t2, and we know that y at t1 is 1 by epsilon into expected value of x into t1 plus epsilon minus x of t1. This is the first y of 1 multiplied by x of t2 plus epsilon minus x of t2. So this is the Poisson increments. Now there is one more process. Let's try to see the third process, that is Poisson impulses. So we define the impulse function here. So Poisson impulses. Now here the stochastic process is, we define a stochastic process such that z of t is a stochastic process where it's just a differentiation of x of t, where x of t is again a Poisson process, or this can also be viewed as the y of t in terms of y of t, where limit epsilon tends to 0 y of t. And if we plot the graph for Poisson impulses, it's just the impulse train, that is impulses at different time t1 t2 and so on, and this is z of t. Now let's try to view this property, the different properties for this stochastic process. Now let's start with mean again, which is the expected value, that is nz of t. Now nz of t is same as the mean for y, that is for Poisson increments, and that is lambda. And we can see that if epsilon tends to 0, there won't be any difference, and there won't be any change in the mean or the average value of the process, because it does not depend on the epsilon. There's another way we can see that the mean value is lambda. That is, let's try to see some other method. That is, nz of t is equals to expected value of d dt of x of t. And we know what is x of t. It's just the expected value of a Poisson process, and the expected value for the Poisson process is lambda t. So its differentiation with respect to t gives lambda. So this is just another method for obtaining the mean value. Let's see the autocorrelation function for this process. Autocorrelation function is just the multiplication of the expected values at time instance t1 and t2. So same way here we can show that at time t1 and t2 the expected value of x of t, and we know that the values of x of t, it's just this at t1 and x of 2 at t2. So this is nothing but we can view this as, we know what is this. This is the autocorrelation function of the Poisson process. So this is d1t dt2, and this is r x t1 t2, which is, we know the value for the Poisson process. That's the autocorrelation function for this process. Sorry, not the expected value here. We just differentiate it with respect to t1 and t2. So this is lambda square t1 t2 plus lambda of minimum t1 t2, and that will be differentiated with respect to t1 and t2. So if we first differentiate it with respect to t2, this will be lambda square t1 into lambda, and this will be the delta function. We know that this gives the delta function. So, and when we again differentiate it with respect to t1, that's again going to be differentiated, and that gives us the impulse function at time t1 minus t2, that is lambda square. This becomes 1 plus lambda, and this just gives me delta. So this is for the Poisson impulse function. The next process is the semi-random telegraph function. That is the semi-random telegraph function. we know that what is a telegraph. What do you mean by semi-random? So semi-random here means if we know the value at particular instant of time, for any given instant, if we know the value of the stochastic process, that is semi-random, that we selected a time instant and we see the output at that time instant. Such process is semi-random function. Now let's try to view this process. So the stochastic process related to semi-random telegraph function or telegraph signal is the stochastic process here is defined as x of t is equals to +1 if k is even in time interval 0 to t, and if k is odd in time interval t 0 to t, the value of such a stochastic process is -1. So it's easy to view such a process in the graphical manner, that it's just going to increase or decrease at each instant depending on the number of. So if in each interval it will measure the value of k. If it's odd, it will have a -1 value at that interval, and if it's even, it will have +1 in the following corresponding interval. Now let's try to see the probability mass, that is the distribution function of such a process. Now let us try to first recall previous formula, that if x of t is, let's say, has value 1, that is k is even in 0 to t time interval, the value is just the multiplication of the probabilities from 0 to all the even numbers, and we know its value, it's e raised to minus lambda, and it's given by the Poisson process. Its distribution is same as the Poisson process, but it's just selected at a particular time interval. So we'll have its distribution if x of t is 1, that is k is even in the given time interval. So we'll have its distribution as something like this: e raised to lambda t into cos of hyperbolic function lambda t. And let's try to view, these are the two formulas that we'll need to prove, or we'll need to find its mean and correlation. That is cos of hyperbolic lambda t plus sine of hyperbolic lambda t is e over lambda t, and similarly this function has the value e over minus lambda t. So let's proceed in the similar manner and let's try to find its mean value. So the average value for such a process can be given by, it's just the probability of 1, that is +1, into p of xt1 into xt2 plus the probability that it's odd, that is -1, into probability of x of t1 into t2. And we know each of the values here is x of t1, t2. it's e over minus lambda t cos hyperbolic lambda t minus e over minus lambda t sine hyperbolic lambda t, and this gives me minus e over minus 2 lambda t, and this is the mean value for semi-random telegraph function. And the autocorrelation function, so we can see that here that the mean value is the exponentially decreasing or exponentially decaying function. So if we average over the time, it's just going to decrease exponentially. And one more, and now let's try to prove or find another property for stochastic semi-random function, that is autocorrelation function, which is the expected value at two instant t1 and t2. And that is just expected value of x of t1 would be nothing but in time interval t1 to t2, if it's going to be if k is going to be even. So even for even in time t1 to t2, it can be said that and for x2, x of t2, we have the function as e over minus lambda t1 minus t2 sine of hyperbolic lambda t1 minus t2. And one more thing here, we have considered that t1 is greater than t2. So this will give me e over minus 2 lambda t1 t2 minus t1. And similarly, if t2 is greater than t1, we'll have e over minus 2 lambda t1 minus t2. So the autocorrelation function and the mean function are just the exponential function of lambda, that is the average rate at which the telegraph signal is coming, or that is the k is even or depending on k is even or odd. Now let's try to view another process, that is a random walk. Now random walk is somewhat similar to tossing a coin. It's just tossing a coin and finding the probability at each time instant. So here for a random walk, let's take the example as tossing a fair coin infinite times, and then based on the results of those trials will derive a stochastic process. So, and such a stochastic process can be given as nt. Nt here is nothing but let's say it's n is the integer, and we can explain more by graph that at different time instants what would be the value of the process. So x of nt would be ks minus nks. Now let's try to see what this function is. Now k here. Now if we say that this is a process of tossing off a fair coin infinite times, then x of nt is defined as ks minus n minus ks, where k is the number of heads, n minus k is n is the total number of times that we toss a coin, and k is n minus k is the number of tails that we receive. So this is nothing but 2k minus n into s, and x of t is nothing but x of nt. That is, we know that this is different time instant 1t, this is 2t, 3t, and so on, and it goes to nt. It goes to nt, and this is just the value of each sample. Now we already know that that if we toss a coin large number of times, that is, let's say n number of times, then the probability of getting heads or tails is given by nck 1 upon 2 over n, and from this we'll find the probability mass for this random walk. So the probability mass for a random walk can be given as probability of x of nt, which is nothing but, let's say, rs here, where r is nothing but the total number of, this is r, that is total number of heads plus tails, that's simply the r. So we can say that k can be given as n plus r over 2, and we'll try to explain that how it comes. So if we equate this p of 2k minus n equals to r, we'll have k equals to n plus r by 2. So from this we get the value of k, that is n plus r by 2, and from this, instead of k here, we have k equals to n plus r by 2. So this would be, sorry, not 2, n plus r over 2 into 1 over 2 raised to n. So this gives me the probability mass, or the distribution for tossing a coin infinity times, and the process is a random walk. Now let's try to view the expected values, and that is the mean or the expected value of such a process. Now before we move on, we define a random variable. Y of t, and let's say yi of t, that is ith time what is the mean when the coin is tossed I times. So at time instant, the time instant would be I into capital T, that is capital T increment of the time. So this will give me the time instant, and this will give me the value at each time instant. And let's say for its value to be plus s and minus s corresponding to head or tail. If it's head, its value is s, and if the toss is a tail, its value would be minus s, where y of it is a random variable. So now we define the properties for such a random function or such a random process. So first property is its expected value or its average or mean, which is the expected value of yi of t, which is 0. And we can clearly see that it's 0 because over a large, when we sum out over a large interval of time, the positive and the negative instants are going to be equal and opposite, so the average value would be 0. Now let's try to see its y squared t value. Y squared t value would be s into s, that is s square. Now let's come back to our original function x of nt, which is summation of I from 1 over n to y of I. So this is our original function. Our original function is x of nt. Let's not forget that. Now let's try to view the expected value of x of nt, and that would be expected value of summation of I over yi, and we know that yi has the average value of 0, so expected value of 0 would be definitely 0. Now for x square of nt, we have summation of I over 1 to n s square, that would be n times s square, and that is ns square. Now let's say the coin is tossed n times and m times. Sorry, not n times and m times, but in order to find its correlation function, the expected value at different time instants, that means, yeah, first time we toss a coin n times, and second one we toss the coin at m times. So that would give me the expected value of sum of I from 1 to n of yi into sum of yi from 1 to m. and that would be nothing but ns square plus e of I plus n to, let's say this is one variable, and this from n plus 1 to y of m, and we know that this both are independent because it has no common elements sharing between them. So for m less than n, we have the expected value of x of nt into x of mt as ms square, or for m greater than n, it's ns square, and we can write it in the general form as well, that expected value would be nothing but minimum of n and m multiplied by s square. Depending on the value of m and n, it would be minimum of n or m, minimum of an nm multiplied by s square. One more process, that is Wiener's process. Wiener's process is it's also known as the Brownian motion. Now this process we can view as the average energy of all the particles moving in a random fashion, and we define Wiener's process as also Brownian motion. So Wiener's process can be viewed as or defined as a limiting process of random walk. That is, Wiener's process has the following limitations, or it's limited to s tends to 0, t tends to 0, and n tends to infinity for given x of t, where x of t is as defined earlier in the previous random walk. So for a random walk we know that expected value of x square t was ns square. And now let's try to find the second moment of such for Wiener's process. So for Wiener's process, what would be the second moment w square of t? That is limit e of x square t with the following limits that were defined during the definition. So with the same limits, we know that the expected value of x square t is ns square, and we know that now yt, t is nothing but, that is small t, that is at any given time instant its value is capital T into small n. So here limit, and we know that nt is t, so t into s square by t, and this limit, that is limit s square over t, will give me some constant value alpha, some constant, sorry, this is some constant value into t, that is the small t here, into t, that is alpha t. So let's try to view the density function, the average value, and different properties for a Wiener's process. So let's try to view the density function of a Wiener's process, that is, let us define Wiener's process. For that, we define a second order density function where it's the function of w as well as t. So this is given as the probability of w of t less than or equal to small w, where w we know that it's a random variable, and for such a random variable it's given as the limit of, as defined earlier, and one interesting thing that is being introduced here is this value, that the constant was found to be 1/2 plus the error function of rs over root ns, where this function is evaluated over rs equals to w. So we can write this as the error function of w over root of alpha t, and alpha was limit n over t, that was defined earlier. Alpha was limit n over t, the constant that we received earlier. And let's see how root ns led us to root of alpha t. We know that we received a root n into s, so it's nothing but n into s square, and we know that nt into s square by t, and we know that this constant, and we also know this constant. Sorry, this is alpha. Sorry, this is s square over t, and this is alpha, and this is small t. So this is t into alpha. Now let's try to find the density from the distribution that we found earlier, which was 1/2 plus the error function of w over root of alpha into t. So differentiating it with respect to w, we get 1 over 2 alpha t into e over w square 2 alpha t. And here one interesting observation, that it's equivalent to the normal density. So the Wiener's process density is the normally its normally distributed density function, and whose average value is 0, with the 0 average value, that is x of t, and we know that x of t has the expected value has the value 0. And the last thing here is the autocorrelation function, which is the limit of Rx t1 t2. We know the autocorrelation function for Rx, that is limit minimum m comma n into s square. So this is limit minimum function of now introducing m and t, that is mth instant and mth instant. So m and nth instant into s. So this is nothing but the minimum of, let's say, the nth instant as t1 and mth instant as t2. So this is the autocorrelation function for Wiener's process, the minimum of t1 into t2 into s square, which is very similar to the earlier defined process, that was the random walk, where we received something similar but not very similar. It's not completely same, but it's almost similar to what we received for the random walk. So for the Wiener's process, which has some limitations, that s and t tends to 0 and n would be very large. So these were different stochastic processes. Thank you.